Okay, we are going to start the session. I wanted to try to explain easier as possible. It's like a kind of quick start for IoT kind of things and WebAssembly, right? So pretty basic stuff for somebody that maybe doesn't know anything about Kubernetes, nothing about WebAssembly and that kind of stuff, right? So, well, I am from Guatemala. I am a professor, also work as a DevOps engineer and a CNCF ambassador too. An author of a book about edge computing with Kubernetes, right? So my background is more as a DevOps engineer than an IoT engineer, right? So let's understand the edge. Edge computing in general refers as simpler as how you are going to process the data. So let's say, for example, in this place there is a server, there is another device that is generating or capturing like humidity, some data from the weather stuff. So you are going to send that information to a server locally to this room, right? So you are going to process the information where it's near to the source of the data, right? So that's edge computing, process information near to the source of the data, basically. It's not like something too complicated. It refers more about where you are processing the data, right? So where is the edge? That's the question, right? So let's think that this mountain is inside this room, and you have a server, a tower for communicate, maybe the server to the internet or something, and there's a user, and in some place there's a device with a sensor, right? That maybe here I have a small device that I am going to show you with the camera. But let's say that this device is capturing like humidity, temperature, that kind of information. So the edge is like, because it's like you are close to the source of the data, it's in some place near to the server and between the device, right? So that's the edge in general. So we are going to use, for example, in this talk, the Raspberry Pi and the Raspberry Pico, because it is simpler to use, cheaper, and maybe you can experiment that in your home, right, with a Raspberry Pi. ARM is pretty important on this kind of scenarios because consume less energy, and it's pretty, let's say, powerful in the way of the context about how many energy is using this device, right? So ARM is pretty balanced. That's the reason that we are using ARM microprocessors in the smartphones, right? Because don't consume like a lot of energy compared with an Intel processor. So it's like better in this case. Raspberry Pi has some models that use ARM in different versions. The ARM V7 is an architecture that is used for 32-bit applications. And the V8, that is a Raspberry Pi 4B, and now the 5, that was released a few months ago. Is designed to process on 64-bit applications. And you can use different kind of operating systems for these Raspberry Pis, like Raspbian, Ubuntu, or maybe the Linux distribution that you prefer. So Raspberry Pi, the Raspberry Pi is more like a microcomputer, use a microprocessor, but the Raspberry Pico is a microcontroller. So it's different, right? You have a limited amount of RAM memory, and it's more specific, and let's say that you can perform like high consumer CPU processes that process information about or do some high performance computation like AI or that kind of stuff, right? So Raspberry Pico is a microprocessor. I think that 2 weeks ago was released the Raspberry Pico 2 that has a new microcontroller with more RAM that you can play on there, right? So how we can reuse the code, and how we can make it portable in some way that you can move your code between different devices, different parts of your system, right? So that's where Kubernetes, TinyGo, WebAssembly goes, because right now WebAssembly is like the hype. Everyone is talking about WebAssembly. So I said, let's try to run WebAssembly on each devices, right? So let's start with maybe one of us doesn't know about what is Kubernetes or these concepts. Let's dive on it. So let's understand Kubernetes first. Kubernetes, for me, because I am a professor too, a DevOps engineer and a professor, I can say that Kubernetes is just to create a distributed system, a system that is divided in different places, locations, the data in one side, the data in one another, one server in one side, one server in another side. So maybe we can say that Kubernetes is a platform to create a distributed system, right? In that context. K3s is based on Kubernetes. It's a modified Kubernetes to don't consume a lot of energy and reduce the footprint, right? So it's pretty reduced. So basically what Rancher does in that moment was remove all the unnecessary things to run Kubernetes on edge devices. So basically K3s, the size of K3s is like 100 megabytes more or less. So pretty small, and you can run it pretty quickly. Also Civo runs K3s on the Civo cloud, right? Right now they are moving to Talos. So with K3s, you can scale these distributed systems where IoT devices are connected, and you can scale it to thousands of devices trying to read or process information at the edge with a low memory footprint, right? A way to install K3s is pretty simple, just a line. Obviously, this line is the most simpler way to install K3s because you have to, in real world, you have to set up a lot of things. But in a simpler way to install K3s could be like with this line, with the defaults and everything, right? It's pretty simple to use. So we have to choose an architecture for these clusters. Let's say that, for example, that I can have like a Raspberry Pi here, or maybe a small microcomputer with these Knox devices. So maybe you can choose a multi-node cluster or a single node cluster, like a Raspberry Pi, right? So that's a microcomputer, remember that. Then, when you choose the architecture for your cluster that is going to process the information near to the edge, you have to create the code that is going to run on your device, in the other device that is going to capture the IoT information about sensors and everything. So in that place, TinyGo goes for the main program, let's say, to generate this WebAssembly. So TinyGo is based on Go, of course, because of the name, but is modified to create programs that can run or can be like compatible with IoT devices, or with the small devices, or with microcontrollers, right? Like this little thing here. So you can program this device using Go, but with this modified base version called TinyGo, right? So with TinyGo, you can program these devices. So it's designed for embedded systems, and also you can run WebAssembly on this kind of devices. Because WebAssembly and these microcontrollers are something new that the people is doing right now because of the portability. Let's say that it's going to start giving support for these devices. So maybe, let's say for the Raspberry Pico is not full supported for WebAssembly, but maybe other devices can full support for WebAssembly, right? So it depends on your use case. I choose the Raspberry Pis and Picos because they're cheap and pretty simple to use. So with TinyGo, because it's a compiler for Go, but designed for edge devices or microcontrollers, can give you the power to generate WebAssembly, to generate WebAssembly code, right? So WebAssembly, for somebody that maybe doesn't know what it's about, if you were programming with Java in the past, Java generates bytecode and has a kind of virtual machine learning interpreter to, let's say, read this bytecode and execute something, right? So WebAssembly does the same thing. Has also a virtual machine that interprets the code and executes something, right? So because I was like hesitating yesterday because I heard a lot of sessions about Wasm, I was like, okay, this is going to have similar slides than the other presentation. So I was trying to give something different, right? Or something complementary. As you remember, WebAssembly has this WASI interface that gives you the power to run WebAssembly not just on the browser, and you can run WebAssembly on microcontrollers or maybe another kind of devices. So how you are going to run this code in your devices? Well, first, locally in your laptop, you have to install TinyGo, right? Then, obviously, maybe you can use Visual Code or your preferred editor, right? Then you have to connect your microcontroller, or in this case, the Raspberry Pico, because it's going to detect the Raspberry Pico as a USB storage. It's pretty simple to detect for Windows and also Mac. And then, when you install the TinyGo command, this TinyGo command also gives you the power to, let's say, to program the device with a simple line. This is called to flash the device with TinyGo, right? So let's explain some example code about how to read temperature and humidity with TinyGo using a DHT11 sensor. So here is some code that you can use to start reading from a small sensor that maybe you were using in the university or something similar, or maybe in high school or something like that. So also has 3 pins, one for the voltage and pretty basic stuff. So with this code, you are going to read, let me show you, just that maybe you can have a context. Here is my face, okay. This is the DHT11 sensor, has 3 legs there, and this is the Pico, right? And it's connected to 3 ports connected to the sensor, right? So basically the code is going to show how to read the information on these pins, right? So you are going to read that information, get the information, do the processing, etc., and then send it to the server, right? So how you are going to send the information to the server? Maybe using Wi-Fi, maybe using serial communication, WART, SPI, E2C, maybe information to long distance, 1 kilometer using the protocol LoRa, etc., wherever you want, right? So let's say that right now, with this command TinyGo flash, you are going to install that code on your Pico device. So right now, my code is here. Just let me show you. Let's cancel this, okay. I am going to read from the serial port from my machine connected to the Pico, and it's reading the temperature and the humidity. When I touch the sensor, it's going to change the humidity because my finger has some humidity, right? So it's going to start to change, right? If I don't touch the sensor, it's going to get back to the initial value, right? Also takes like 1 to 2 seconds to start returning. Also, you can check the temperature, right? It's returning to the previous values, right? Because I am not touching the sensor. So right now, you have your device with the program, and you are monitoring the values that this sensor is getting, right? So you have already programmed your device. So let's move for the server. Okay, this is how it looks, right? When I was showing with the camera, but live, right? This is the Raspberry Pi, but this is a 3-node cluster using K3s, but I was like just using the one of the bottom, right? Only one. Okay. So also, maybe Go could be some complicated for somebody new. Maybe you can use MicroPython. MicroPython is based on Python, but has libraries to configure your device. Also, I think that has more support for different things on a Raspberry Pico. And it's supposed that a Raspberry Pico and a Raspberry Pi is used just for prototyping. But some people use this for production, right? So let's move to Wasm. So right now we have our device prepared to read information. WebAssembly, as I mentioned, maybe could be like a kind of style of Java generating bytecode, but this is different, right? It's more portable, has more speed and different things, has a lot of features that the people is interested with their data. Also, WebAssembly use a stack machine designed to encode information and perform all the calculations and the executions. But what is a stack machine, right? So this comes on virtual machine types. If we remember Java, in the beginning, Java has the Java virtual machine, the JVM, right? So the JVM was using registers directly to the CPU, right? So uses the registers to do calculations and that kind of stuff, right? So let's say that this is the way to interpret and execute the bytecode using the registers of the computer. But because Wasm is a stack-basis VM, it's different. Use the stack to put information and do the calculations. Yeah? So it's a little bit slower in some way and less powerful than the Java virtual machine. But it's more faster that, for example, run directly Python code. So some people, for example, use Wasm bytecode and read it in your code to interpret information that is faster than running something on Python directly. Yeah, so that's the benefit, the speed. Some features, as you know, a lot of people mentioned in this session the WASI. WASI doesn't run the Wasm on the web, run Wasm on a runtime, right? Like a kind of the Java virtual machine, but we will like the Wasm virtual machine, something like that, right? So WASI gives you that power and the interface to run these kind of things. So one of these runtimes to run Wasm could be WasmEdge, that is designed to run WebAssembly on the edge, right? So it's pretty lightweight, designed to support ARM microprocessors, because you know, when you are compiling a container, you are compiling the thing for Intel, but usually on edge devices, you are using ARM because they use less energy consumption. So the challenge is to compile your code into an ARM microprocessor. So WasmEdge support ARM for this, right? So you are using WasmEdge to run your bytecode or WebAssembly bytecode, let's say. That gives you the power to run that on the edge, right? On the Raspberry Pi, let's say. But also has a lot of benefits like security, fast execution compared to the native execution on Python, pretty portable. So the idea of this is like Java, compiles once, runs everywhere, says, right? You remember that part of Java. But this is compiles once, runs everywhere, where the runtime is installed, right? And is supported for that architecture for microprocessors, right? So there are a lot of applications, a lot of things that the people is starting to process the information near to the source of the data, called edge computing. So how do you do that part, right? With TinyGo and Wasm, you are going to create your portable code for IoT and edge devices, but how? But let me explain you what it means WebAssembly for on the context of edge. So Wasm on the edge means like the ability to perform on-demand computational intelligence in the right place and in the right time. Where? At the edge, right? It's secure, it's a good performance, reduce also the latency. Instead of going your data to the cloud and wait for the response, you are sending the data locally, let's say at the end of this room, and it's going to send me the information using Wi-Fi of a regular cable, right? Of Ethernet. Something that I extracted for somebody that is pretty important in this context. The DET program is a guy that works on TinyGo and microprocessors and that kind of things. So he mentioned this part, like why WebAssembly on embedded devices, right? So I extract that part. and he mentioned that it's pretty extensible because each WebAssembly file could be like a kind of module that you can load in your program and could be executed faster, right, compared with another devices. Also, this runtime, as you know, the Java virtual machine in the past was considered as a container, right? The old containers. So Docker is using the concept of container, but the containers existed previously, right? So just Docker will become popular because it has like features of committing the code, committing the images, and that kind of stuff, right? So it was a boom when that happened. Also, WebAssembly on embedded devices could be like pretty nice to update your devices or add more modules or update the modules. And you can generate the WebAssembly using different languages like Go, Rust, also Python, and there are support for a lot of languages. So it's becoming like the new standard for portable code between different platforms. And the life cycle, you have your code. With the compiler, you generate the WebAssembly language. For web, you are going to put this on an HTML website, and it's going to be interpreted by the browser, right? And in the other context of the edge, you have the code, the WebAssembly, and you are going to run this on a runtime. Which runtime? WasmEdge, right? Is one of the runtimes that you can use. So let's say, for example, that you have your code, you use the compiler, you generate the WebAssembly, and in this case, this square is representing the Raspberry Pi, okay? It's going to be interpreted by the runtime, and it's going to read information and wherever you were programming in that place. The code, the simple hello world. Here is the magic, where the magic comes. How to generate a container that can run this code. This is the trick. This is the 1 million code, right? You have to install the WasmEdge runtime, send the Wasm generated them, and send it to run the code when the container starts, right? In this way, you are going to run the WebAssembly on a container. And this container, you can install it on regular Kubernetes or K3s, right? And you can put like small pieces of code just to be executed in ephemeral way, like a kind of serverless functions, right? So in that way, you are going to reduce the energy consumption too. How? Maybe you don't want to use these frameworks like spin something that mentioned in some tag and that things that are automated. If you want to do it manually, because sometimes for edge devices, it's too much, that frameworks, you have to deploy the thing in this way. And the magic here is that you have to give permissions for sysadmin in the operating system, right? And in this way, it's going to read maybe another devices like cameras, like sensors, and that kind of stuff, right? And you are going to run the image in this way with a simple pod. This is the test about that is going to run on ARM. As you can see, the uname is giving information about the kernel. It's using an ARM64 on an AWS machine. So it works, right? So you have to create your own code because your own necessities, right? So maybe you can use Grafana to visualize your data about your devices or the thing that your system has to perform. So in general, this will be the architecture. The same thing, the device, your code, how it's going to be interpreted, where to storage the code, running on a microprocessor, and here on the microcontroller, right? This is like the general architecture of how to run WebAssembly on the edge, right? Using TinyGo or whatever language you want. That's an interesting combo for the serverless Knative plus Wasm, right? Knative is a kind of Kubernetes serverless platform. And what else? A simple use case. This is a scenario, reading information from some sensor, a database, maybe you want to send information to the cloud, etc. So it depends on your own use case. some reference if you want to take a look, more information, but at least you want to play a little bit with TinyGo, K3S, and here's a couple of examples, the slides if you want, and my book, my book about edge computing, and that's it, and my contact. So that's all. If you have questions, I don't know.
We don't have the time for questions. So
Okay.
maybe one.
Only one, okay.
I played with TinyGo on ESP32 and Wi-Fi never works with TinyGo unfortunately, but my question is, with your Docker container, you start that fresh every time, or it handles the request like it's a long-running Docker container, but the Wasm functions are created new each time, or how does that part work?
I think that you can, well, you can create the WasmEdge as a daemon. So it's like hearing in an API, let's say. So you can create an API that is going to request your Wasm code and execute the Wasm code in your container. Yeah.
Because also in a cluster, I think you can put that this is the heavy part.
Yeah.
Okay, gotcha. Thank you.
Yeah, I think that's it. Thank you very much.